and swimsuit and towel.
Somebody said that there's algae, but you can bring a
Really?
bring also a coat. You can bring your kids. I'm bringing my kids. If you have your kids or your family, you can bring them. That's it. I'm gonna get off the shoot.
You ready? Yeah. Great.
Okay, the next talk is going to be by Joao Correia. I guess about how many AIs do you want?
Exactly. Yeah, I'm João Carreira, as you said. I'm a research scientist at Google DeepMind. I would like to thank Shiri and the organizers to invite me here. I have another 10 to add to this title. I was a postdoc here 10 years ago, so it's great to be back. And my title was a bit cryptic, but it reads as 10 AIs or 10 billion AIs. It's like a choice. Okay, so as we've clearly seen this week, current AIs, they're amazing. They're like incredible polymaths. They may not be up to the quality of the experts in each field, but across the board, they're on average perhaps superior to any of us from a chat interface perspective. Models like Gemini, ChatGPT, Cloud, and so on. They're also multimodal, increasingly so. For example, the latest Gemini can take in chunks of text, interleave with chunks of audio, chunks of video, images, and so on. And there's now even demos of speech-based such systems where you can just interact naturally with them. But the usual criticism anyone will throw at these models is that they're very expensive, very high energy consumption, very bulky. And one I don't really like is that they don't really learn post-deployment, right? So they're like these frozen polymaths in a sense. So you can interact with them a little bit and they'll do some in-context learning, but next week you go back, they forgot all about it. And another aspect is that they're quite similar. So there was this post from, I think, one OpenAI researcher called the IT in AI models is the data set. And what he observed when he was training lots of different models where he was changing the architecture, changing the optimizer, hyperparameters, but it was always the same data. All the models are the same. So if you have a sufficiently large model, the AI is this function which is defined by the data, right? So the data is the model in this set. So yesterday's AIs, like in this movie, the Short Circuit, I hope that they'll be tomorrow's AIs as well. So since Shiri gave me lots of time for this talk, I'll show a minute.
Malfunction. Need input.
Input. All right, right. You got it. Okay. This is a house. We live within it, inside it. We have a floor, see? And
Good.
we have the opposite of a floor, which is a ceiling. Look up.
Ceiling.
We have here, Oregon.
Oregon.
Home of the beaver, famous for cherries.
Beavers. Cherries. Input.
I'm giving you great input.
More input. More input.
How about pictures? Do you like pictures? We have a lot of pictures here. A lot of them. This is a picture of an aardvark. See that? It's an aardvark. It's a mammal.
Input. Aardvark. Abyssinia. Adam.
Holy crow! You can read.
I don't know. I found this very memorable the first time I saw it when I was a kid. I still remember this speed reading thing. So I guess it's kind of like how current models are trained. It's like speed reading the whole internet. But yeah, I envision a day where the models will be with us and we can just teach them through long time span.
Malfunction.
Malfunction. Okay, so tomorrow AIs, I think they'll be embodied, right? And they'll learn from a single stream of experience from their sensors. And okay, perhaps more controversial, I think they'll have a minimum capability out of the box, which is the ability to learn. So yeah, maybe some people prefer models that have a bit more capabilities, but I would aim for this one, which is a bit like children and animals and so on. And they can come in different formats. It can be a little Tamagotchi you take around. It can be a car, it can be your car. It can be a little pin you put on your jacket, as I know there's a startup here. Or it can be legged robots, wheeled robots, or they can be all of these at once as well. And my expectation is that everybody will raise their own models, a bit like children. They'll choose how to educate them by taking them to school, the movies, show them certain music. And one advantage is that there will be no need to unlearn many things as currently there is. So currently the models see the good, the bad, and the ugly of the internet. And then it's a bit of a hack-a-molly work of trying to get rid of many bad things we don't want the models to have. So this won't be the issue if you're learning things more or less like tabula rasa. And yeah, going back to the title, the 10 billion AIs is that everybody can have many AIs at that point. So okay, why I think this would be valuable? So one thing that happens with the current models is that we're force feeding them all these human concepts, things like every year the cycle of the weather repeats, things that a human eventually discovered by himself. It created this knowledge from his senses, or things like a cat has 4 legs. So what I would call here, so if the models are able to discover these things, they would be more like world model makers, not just world models, as we discussed here. So I think this is an important capability that is not clear that current models have of creating this knowledge. We're just like distilling the human knowledge. And also connects a little bit with Lucy's last slide, I think, of restricting a little bit the data set and so on. And if you have many different models, each having its own experience, going back to that argument about the model is a data set, then we would have a large diversity of data, hence models. And they can also have different sensor configurations, so they'll have different views of their own experience. So this will give rise to a true species, also going back to Lucy, with many different elements, not just a species that it's really like 1 animal or 10 animals. They're all very similar. So this will give rise to diversity, which is good in biology. And finally, more of a commercial argument. I think people will prefer this type of AIs. People like to have control over who lives with them, their children. They like them to have their same language, same, like the same type of music, the same club, politics, religion, whatnot, which is impossible with the current models. Someone else decided all these things for the existing AIs. And finally, big companies these days are doing a lot of data curation. That's the main thing they do. If we offload the data part to the people, then we can just focus on the science ourselves, both companies and academia, focusing on improving the hardware, the core learning capabilities, and the everyday people do the data part. Right, so why doesn't this exist yet? There are many technical challenges. First of all, the entry-level problem, I think, is just learning from a single stream of experience continuously. So we don't know how to do that yet. But there are the problems, efficient use of computational resources to deploy them in small devices, adapting to arbitrary sensor configurations, problems that have been discussed before, acquiring language from raw sensory streams doesn't exist just yet. Social skills, action that I didn't work on, so I won't talk about. So I'll focus on learning from a single stream of experience continuously. Yeah, feel free to interrupt. My talk is not very long, so there's plenty of time as well. All right, so I'll discuss 2 papers we had recently. One of them came out just in iClear, and the other one in CVPR just last week. And what we did is we start from the standard deep learning setting. We know it works, the large, diverse data set, and using stochastic gradient descent over batches of training examples. So that's how all the models are trained. And then the first question we looked at is, can we relax the need for large, diverse data sets and instead train from a single stream of experience? So that's what I'll talk about first. Okay, relaxing the need for large, diverse data sets. So I guess the reference in a data set from which people learn visual representations is ImageNet. So for those who don't know, which I expect not to be many, it's this data set that took years to collect 1 million images across 1,000 classes. Each class has 1,000 images. And yeah, you saw the birth of deep learning in vision with architectures, but also various self-supervised learning approaches and so on, and it's still very used today. So yeah, the first author on this paper is going to graduate next week, Shashanka. So this was work in collaboration with people also from Amsterdam and other places. And yeah, all the source code and the data is in this link above. Okay, so how does ImageNet differ from Life, right? So if you consider the boat class, on the left, I'm showing a bunch of boats from ImageNet. So you can see that they're all different models. They're seen from different viewpoints with different lighting conditions. Whereas if you look at the right for a regular video of boats, it's very slow, kind of boring, but you can see the same boats from different, that same exact boats from different viewpoints over time with the different lighting conditions and so on. I was just chatting with a friend who's not an expert on this area about how hard it is to learn from these smooth videos, and she was saying, oh, it should be the opposite, right? It should be much easier to learn from these videos rather than like random images from the internet. But that's the current technology that we have. So to study this, to study for learning from these more natural streams of video, we collected a walking tours data set, which are these videos that you can find on YouTube that are very long and very smooth and show people walking around in cities. So on average, we collected 10 videos from different cities that have hour and 40 minutes each. We also did some analysis on how many object classes you can find in each of these videos, and it's around 700. And they're Creative Commons license, so you can use them for research. And we studied them a little bit, as I was saying, by running an object detector on these videos. And you can see that on the left, for walking tours videos, you have around 40 objects per frame. So this was run on 2 hours of video. So you can see over time how it varies. And they compare to Epic Kitchens, which is an egocentric data set of someone wearing a camera in the kitchen. You can see it's fewer, it's a more restricted setting in a kitchen, whereas these are like high-resolution videos outdoors. Or comparing to Ava, which is made out of movies, so significantly less objects. And we also got this movie from YouTube, a romance, called The Night We Met, that's in red. Very, very few objects as well. And if you want to look at the diversity of object classes in these videos, that's on the right. You can see that Walking Tours has, this particular video has up to 600 different categories. It's a long tail, so most categories are probably people on the left, but it's still quite diverse. It's not 1,000, but this one video had 600 categories. So seems promising when comparing to, say, ImageNet. And another property of these walking tours is that they're very smooth. There's not a lot of shortcuts. So if you go to this romance we got from YouTube, you can see on the right it has lots of shortcuts. So people, like the style of filming, there's a lot of movement from one person to the other when they're speaking and so on. Whereas these walking tour videos over cities, some of them have no shortcuts. It's just continuous, one stream. And some have a few, but not many. So this is good if you want to exploit continuity in videos in your self-supervised learning approach. Okay, so what we did in this paper was to propose a variation of Dino. So we heard about Dino, I think, from Michael's talk yesterday. It's like a SOTA method for self-supervised learning from ImageNet. And what we did was we started with Dino. We did some adaptations to work with video that basically tried to track multiple objects in a self-supervised manner throughout short clips of video, say 5 seconds long. So the way this works is we sample a 5-second video, and then we sample a pair of frames within those, pass it through a teacher network, and then pass it through a multi-object tracker, which is, it's not like a pre-trained model, it's like a bunch of layers, transformer-type layers that produce masks. They produce, say, 3 masks per frame, which are supposed to be like objects tracked over time. Then what happens is we mask the original images with those masks, and we pass the mask frames through a student network. And then so the loss imposes that the student model should be able to predict from these masked frames features that correlate well with the teacher model that saw the whole frame. So that's the kind of the typical approach in Dino as well, but here we have this masking over time, like a tracking. Then, the teacher network gets distilled from the student. This is the standard, also Dino approach. Right, so that's the rough idea. So exploiting video in Dino and exploiting continuity in time in this self-supervised learning approach. And I'll just give a little sneak peek into the multi-object tracker. Don't get scared. So it's worse than LSTMs. It's a PhD student had time, and he increased the complexity a little bit. But I won't try to describe it. But the one thing to retain is that so if you don't do anything special with this, multi-headed attention and so on, the masks would be overlapping. So we imposed a little layer there that makes the masks not overlap, something using optimal transport technique called Sinkhorn-Horn, or just Sinkhorn, yeah. Okay, and then if you do this, you train on this whole video, hour-and-a-half long video for a while. You treat it as a data set, so you're sampling randomly clips and doing this thing I just described. You get these nice emerging attention maps in this method we call DORA. So you can see here we have 3 different masks. One is latching on nicely to the person standing by the road, and the one to this moving light post, and the person on the bike. I have another example here. Also 3 nice object maps, one on 2 on people and 1 on the bike. One may ask, are these object type regions useful? And we compare them to random blocky masks, and they seem to bring large improvement, both for image classification, like ImageNet, so that's the LP there, and for a localization task on the right. So yeah, object masks do help performance. And if you compare Dora with Dino when pre-training on various video datasets, not just walking tours, there's an improvement across the board, but it's especially pronounced for these walking tours videos that are long, very continuous. And finally, going back to the initial question, is one video as good as ImageNet pre-training? It's quite competitive. So you can see that most tasks is similar performance or slightly better. There's one that is a bit worse, this object tracking for some reason. And yeah, overall, it's quite encouraging. So maybe you don't need to collect a data set for years, very diverse, highly controlled, and maybe you can just send our robots outside for a walk in the city for an hour or 2. And it's encouraging to this whole story I was saying in the beginning of moving to a single experience stream. Yep.
Do some walking tours work better than others?
Good question. I would have to check the paper again. I think there's not much difference. It may be correlated with this shot boundary. Some of them have up to 10 shot boundaries. Yeah.
Can you explain whether you have a heuristic, right? That Dino seems to be better?
Yeah, it doesn't help the story much because the model, this one is actually trained for tracking. I wonder if it's because of the boxes. So the last one, the last arrow on the right, it's also tracking, but segmentation based. So and this object tracking is box based, so it's quite specific. I wonder if it's because of that, but I don't have a good answer.
Do you think will help you to put into Dora?
You mean putting boxes there?
Yeah, or something like that to help you.
Yeah, maybe. Okay. Possibly, but it's not super clear that we care too much about bounding box tracking. Typically, yeah, it's kind of an older task. So if you can track based on segmentation, like the last task on the right, that's more interesting. It's more precise.
Thanks.
Yep, you too.
So I have a question about the masking strategy. We were talking about future object. You were also talking about like you use multi-head attention as some strategy. We know that multi-head attention, different head tends to attend to different object, right?
Yep.
But I'm still a little bit confused. So did you mask out the whole object, or you find out by your method, or like what exactly were you doing?
I mean, so it's kind of emergent. So we don't decide to mask the whole object, whatever.
So as long as whatever the multi-head attention attend to the area, attend to, you mask them out.
Yeah, exactly. So
Okay.
we mask whatever
Yeah,
emerges.
that makes a lot of sense because we previously observed that for some self-supervised learning, the multi-head attention used to tend to some either parts or either like objects if
Right.
your self-supervised learning is trained well. Okay, thank you.
Right. Okay. Right. Okay. So again, as I was saying in the beginning, this is like part of the problem that we want to solve. So it was a single stream, but it treated this stream as a data set. So it was shuffling the clips, doing aggressive rescaling augmentation like Dino usually does, and using large batches. So now we would like to do that, but watching the video is a natural stream, so continuously and sequentially, and say 24 hours continuous stream without augmentation and with batch size 1. Okay, so this brings me to the so-called engine of deep learning, stochastic gradient descent. This was probably like the main result back in 2011 or so, that you could just do stochastic gradient descent. Don't worry about local minima. Don't worry about optimization issues. Just do it. So the way it works is you want to optimize this loss function over a whole large data set, but it doesn't fit in memory, so you just take a random subset of that, and then compute the gradient on that, and just keep going, right? So this is so-called so it needs to be random, so it needs to be independent, identically distributed data. That's a big part of SGD. So the batch size is kind of a detail, doesn't really matter. So batch size 1 should work. It's just the IID part that matters. And in fact, Jan LeCun had this tweet saying that you shouldn't train with large batches. That's bad for your health. And there are papers showing that small batch size is actually good for regularizing your model and so on. Yeah, so the issue is IID data, that in ImageNet, there's no problem. You sample randomly some images, you have IID data. But if you look at some of these data that, for example, we saw yesterday, SayCam and so on, heavily correlated frames, the same colors, the same objects across large periods of time. And yeah, Viorica ran this nice experiment where she was comparing the similarity of consecutive gradients in the case of a continuous video versus a video with frames randomly sampled. And you can see that the IID case, there's a nice Gaussian around 0. They're very decorrelated, whereas in a continuous video, the gradients are very correlated. And what happens is that if you just use standard techniques for optimizing a function with this type of data, the continuous case just doesn't take off. It's just dead there. Whereas with IID, it does optimize nicely. Okay, so there's a discipline that studies these problems. It's called continual learning, but they don't really consider usually this more realistic case. What they do is they say go to ImageNet and then sample a class. Then they train for a while on that class by sampling randomly, say, cats from that class. And then they move on to a different class, and then they want to test if they still remember the first class. So, but there isn't this correlation of gradients that we have in the continuous video case. And yeah, Alyosha did some of the most relevant work here on test time training on video streams. The setting there is you train some model. Now you have a test example, and you optimize some self-supervised loss, and this usually leads to better performance on the original task. And there's also one related paper by Abhinav that has one of the sections focusing on learning from a continuous video stream, but not in very large detail, and using like a replay buffer technique, which is kind of reducing the problem to supervised learning. So basically, as you go through the video, you just keep adding samples to your buffer, and then you sample randomly with a big batch. So people in continual learning don't see it as very satisfying intellectually, and it's also not very efficient. You need these big batches that make it slow. And it's not scalable over a long time spans either. Okay, so this brings me to the paper we just presented last week at CEPR, learning from a continuous video stream. So the idea there was to create these continuous streams from existing datasets like Ego4D or ScanNet. So Ego4D has longish videos up to 2 hours, and ScanNet has just 5 minutes each video, but we concatenate them into like a day long video to train our models. Oh, let me show you ScanNet as well. So ScanNet doesn't have moving objects; it's just like scenes. Ego4D is egocentric, and there's like all kinds of things there. So we experiment with creating 2 different types of streams. One that is continuous, where we concatenate these smaller videos, shown on the right. So imagine you have this red video and this purple video. The continuous stream would be red and then purple, whereas the random stream would be all colors there. And we set up a
In the continuous stream,
it's
still just one pass through the data, or there are multiple passes?
So for Ego4D is 1, because we have enough data to do like a full day of video. For ScanNet is almost, so it's like 20 hours. So we just do 4 hours where it goes back to the beginning. Yeah. Okay, so as part of this framework, we set up also a few tasks around future frame prediction, either in the pixel space for Ego4D where we don't have annotations, or in the semantic segmentation space, so you have some annotations for the various objects, or in terms of depth. And we either predict the present, which makes sense for segmentation and depth, but not for pixels because it's trivial, or 4 frames in the future or 16 frames in the future. So we tried these 3 settings. And as I was saying, the model goes through a 24-hour long stream. And in terms of the models and the loss, we adopted also a Berkeley creation, the pixel-to-pixel setting. We tried 2 models, VIT and the UNet. Very simple setting where we input 4 frames and predict 4 frames. So it's not like a long context transform or anything. We simplified that bit quite a lot. And all the tasks are defined in RGB space, so we don't need to change anything. So depth is just a different color map compared to semantic segmentation and 2 pixels. So one of our contributions in this paper is the way we evaluate. So we split it into two parts. One is in-stream adaptation, which just measures how well the model is doing on the stream it is adapting to. So you're continuously adapting, changing the weights for that stream. But at the same time, we get exactly the same model. And at every point in time, we're checking how it's doing on a different stream for which it's not adapting. So this is, we call off-stream generalization. And the idea is that depending on the task and the way we're learning, maybe that the model is learning trivial things about the current scene, say this model, just looking for transparency. So it's just latching onto transparency. And if there's something else transparent in the different scene, it just hallucinates a bottle. Whereas a better model will look at shape, and that will generalize better in upstream. So this paper, we didn't really invent anything. It was more just checking existing techniques on this problem that hasn't been studied much. So we looked into things like optimization, augmentation, existing continual learning solutions, and pre-training. So I can just scratch this bit. We tried things like random cropping as we go in time. That didn't help at all. I thought that would increase the IID-ness of the data, but didn't seem to help. This popular elastic weight consolidation, continual learning technique from DeepMind also didn't work. And we did try replay buffers, but given the same wall time, it didn't seem to help either. So, and it's not something people prefer. So we just skipped that. And so I'll talk mostly about optimization and pre-training now, where we have more interesting results. Okay, on optimization, we did try all the optimizers we could get our hands on. And here are results averaged over all tasks, all time steps, all models. So an interesting thing is that the RMS prop seems quite a bit better than the other ones on this setting. So obviously, Adam is the most popular optimizer that everybody uses, but here it wasn't very good. Then we looked a little bit into why Adam is so much worse than RMS prop in this setting. And it seems like one hyperparameter that matters is momentum. So for those who don't know, momentum is basically like people usually describe it as this ball that is rolling down a mountain of the lost surface. So it's accelerating, and then it doesn't care too much about the local gradient. So once it accelerates, it discards the local gradient. And basically here, the gradients are very correlated, so I guess it gets a lot of momentum. I don't know. I don't have a good theory, but it seems like momentum hurts in this case, which is not the case when you do like IID data.
That would make sense, but your video already has momentum.
Right, yeah.
So you're doubling the momentum.
Yeah, maybe there's some weird change. It just goes off the mountain, kind of. Yeah. So yeah, that was one result. Another thing is related to how often you change the weights. So you can do it every step, or you can accumulate gradients over multiple steps, say 4, 16, or 64, and then update your weights later. And for in-stream adaptation, it seems like updating every step is best. So you get lower error for future prediction and higher segmentation quality for segmentation. But when you go out of stream, so measuring generalization, it's the opposite. So it seems like it's better to accumulate gradients as this leads to more solid representations. So for both future prediction, you can see that loss is lower when you accumulate less frequently, and your segmentation is better when you do that as well. So somewhere in between is best for both, I guess. Then, yeah, we can visualize this here. If you aggregate, so this is showing the out-of-stream performance. If you aggregate steps over 64 time steps, you can see that the resulting color after 4 hours of training for this particular sample is a little more brown. So it's closer to what it should be. Whereas if you aggregate steps, aggregate steps is 1. So if you're optimizing every step, when you go out of stream, it's like hallucinating things that are not there. Probably things that are in the in-stream case. So here's a video showing. So it's just hallucinating various colors over time. Things that are not in this particular stream, but are probably in the other video over which the model is training on. Okay, then that was the optimization part. We also looked into pre-training, and we looked into video-based pre-training, 3 different tasks we tried. as pre-training. So one is called video guided future prediction. The idea is you sample some patches from the future, you replace them in your input, and now aided by those extra patches, you predict the future. So it's like you have some extra information about the future. We also tried just vanilla future prediction, where you just have a frame. Now you try to predict some displacement in the future. And then a harder version of the problem where you mask much of the image. Now you try to predict the future again. And yeah, we compared to ImageNet-based pre-training, where they mask some of the patches and then try to predict those in the same image. So no future there. And yeah, it seemed like guided future prediction was a little better from the 3 we tried, and the bigger displacements also led to better results on kinetics himself. The numbers are not very high because this is like literally a classifier on top of the representation while learning, so it's heavily masked and so on. So the numbers are lower. So there's all this augmentation. It's from a single frame as well, not like from a whole video. So we can see the results of the pre-training for the various tasks. So here is yeah. So on the right, it's mask future prediction. This is the way the input looks. These are the predictions, a little blurry. This is target. So this is guided future prediction. So there's some weird patches at the top that come from the future, and the model tries to predict the future with that extra guidance. And this is vanilla future prediction. It's just predicting the future. Okay, so that's the type of pre-training we did. And now we compared with the ImageNet pre-training. And yeah, so these guided future prediction models did better, say on Ego4D. It's not super surprising. They're trained for future predictions, which is kind of the kind of tasks we use anyway. But I guess the bigger message is that even when you're doing this continual learning over a whole day of video, it's important to have some initial weight. It's a bit like the genes, right? So starting point does matter. And yeah, some more results. So across various tasks, it always helps, the pre-training. Okay, so then these were more like ablations and studies, then going back to comparing with the IID training, right? So we have a baseline we defined here. We call it standard deep learning. It's using Adam, updating weights after every chunk, using this ImageNet MAE checkpoint, batch size 1. And ours, we call it baby learning. We use this RMS prop, update weights after 16 chunks, use this kinetics guided prediction, and also batch size 1. And what we can see is that if you use the standard deep learning in the continual setting, it just doesn't train at all, what we saw before. If you use standard deep learning with IID, it does train well. But if you use this overall baby learning method we had, and this is the case with no future prediction, just temporal displacement 0, so it shouldn't have a benefit over MAE, which is used in the standard deep learning here. So we see some benefit in this batch size 1 case. And both in-stream and off-stream, so the results are the same. And across multiple tasks, same results. And then, yeah, you can ask, what if we bring the IID back to our setting? So unfortunately, that still helps a lot. So yeah, we did some improvement, but IID is still very valuable. So I guess we need to invent some techniques here to do as well as IID. Right, so not a very long talk, but the conclusions are that videos have a lot of information. We may not need the whole of the internet to learn useful representations, and we're just scratching the surface of single stream learning. There's a lot of research to do, I think, and it's cheap. You just need one GPU. It's great for academia. And yeah, the overall philosophy, I think, follows a bit what this quote from Turing. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this was then subjected to an appropriate course of education, one would obtain an adult brain. I guess he didn't have in mind that it wasn't so hard to actually program an adult brain like the large language models. But I still think it's a good idea. Finally, Shiri's requested slide, looking forward. So my question is, what will the loop of single stream learning look like? Right. So for example, in neuroscience, we know that if children have some cataracts when they're born in the first year, they never really learn a full-fledged visual system. Should we have that as well, or is it just feathers like yesterday's talk? Maybe that doesn't matter. So this critical period of learning. Also, like last week, we were talking about these multiple parallel threads, competition, instead of SGD is just one thread, right? Conscious self-improvement, something we also discussed yesterday. Maybe managing different latent spaces. Maybe some of the learning is in this latent space of language. Maybe some of the learning is elsewhere. So different levels of representation. Memory, curriculum, and so on. Yeah, so that's my looking forward slide.
Hi, this is Dara Yu from Berkeley. So I think thanks for the talk. I think it's here, like the non-IID nature of the data is sort of like a bug in some sense. But I'm wondering if like you think there's any kind of possibility for it to actually become a feature. Like if actually there's some kind of like richer learning signal you can get from data that is, you know, like kind of peaky in sort of a systematic way, and if so, like what that might look like.
So I guess the first part of the talk with these walking tour videos, it did seem like, you know, it's not a bug. Like if you have like 5 seconds of video and you leverage the structure, the smoothness, this seems to help. The problem is just that, yeah, it works better if you have like a big batch of very orthogonal things doing that. So that part I don't think anyone knows still how to do it.
So I really like this paper, as I told you, because this is something that I've been trying to do for years, and I think you guys got, you know, it's not all the way, but it's at least you made.
At least we started.
Yeah, it's starting to get there. I wonder what you think about the connection, if you compare this to text data. So in text data, my understanding is that on one hand, the LLMs are, you know, they are processing things in one pass, so that's all good. But I think there is still some sort of chunking. So, for example, you know, you don't read all of War and Peace in one go. You do a little bit of War and Peace, and then a little bit of Twitter, and a little bit of, you know, whatever. But I think that those chunks are quite a bit bigger than our chunks. So, do you know why the text people can deal with much more non-ID blocks than we can envision?
I'm not sure they have a big problem with non-IID in text data. Even within a book, you know, you move to the next word, and it's not the level of correlation we have with the video, like pixels. So maybe, I don't know, maybe other people know, maybe they're working on it.
Definitely, if you know, Tolstoy is correlated with himself, right?
Yeah.
So there is definitely this kind of, you know, I think one book is kind of like one video.
Sure. Yeah, Andrew.
I think the batch sizes are just massive in text because you can fit a lot more books through a TPU or whatever at the same time.
Right.
The videos are just much bigger. So I think it's partly just that you're getting rid of the IID issues by having a huge batch of many different things that are all correlated within a single batch.
So there's also this issue with pixels again, right? Pixels just between two frames is just one pixel don't change. So that's really hard to use. In text, between two chapters and two, most words going to be different, even if the characters are the same.
Right. So do you think that there's an issue with batch size 1 in text? It wasn't trained well?
I think so, but I think John's also right. It's maybe a worse issue with video.
Sorry, people who are listening online. Okay, I was going to ask something different. So we have Uli Hassan who just showed up, and tomorrow he's going to talk about his very long videos from babies, I think. And I'm wondering, I'm asking your question. I'm sorry. Welcome, by the way. I'm wondering if you had access to this type of data, what kind of things do you think that you would learn that maybe you wouldn't from the Ego 4D, which is adult focused?
I mean, I'll be super curious to see if it learns faster. For example, there's all this curriculum theory that you start, there's not much going on, it's just faces and things. So it's pretty nice to test that. Yeah, unfortunately, we don't have access. We're trying to get some access to some of this data, but we're a big company, so.
Yeah, so returning to the other comment about bug versus feature. So my thoughts are if you show a child all these random images, the child cannot learn because the architecture is different. So I assume that you're taking the architecture from what we learned is very good for ID data and for this type of images, right? For this type of video stream. So you change the architecture, maybe it's not a bug.
True. Yeah, I mean, if we have an architecture that kind of aggregates information over lots of frames and has some smoothness assumption, then it would fail. But I don't think most of the vision architectures are like that. They are very happy to take 1,000 different frames in order.
Yeah, so it's a bug of the system we learn about this architecture.
Well, children don't do back propagation, right? So that's the original sin right there.
Well, but if you give them ID images, they're not going to learn as fast as they do with this continuous environment. So it's somewhere in the middle.
No, I think maybe the back propagation is the problem.
But then there's like the Nemo stuff that was kind of like talked about here, where it's just kind of like additive updates in the forward pass.
Oh, sorry. So, but I'm not sure that kind of like solves things, because if you have examples with a lot of pixels, you're just going to reinforce the same stuff over and over and over again in a video, and everything will just go down the drain very fast. I don't know if it makes sense. No? Okay.
Lucy, last question, and you're.
Oh, yeah, sure.
So, Lucy Cheek, Cambridge. So one of the things I was going to say is that obviously in human, like a lot of the stuff in neuroscience has been like looking at how humans chunk continual experience, because clearly we do. And that look, we have like signals for the end of an episode, despite things being continuous, and then information about like what we actually learn about, like relative to where it falls in those chunks. And I wondered if you're doing anything like that to kind of chunk the videos into batches of experience. And the other question, sorry, just was, I think I've missed it. Like, how did you provide the ground truth for what the objects were across the big videos?
Yeah, so we cheated. We used, data sets have annotations. So we had the one setting where we just predict in the future, not using annotations. But are you talking about the second part of the talk?
So just for the things like the walking tours, like how did you tell it what the objects were?
Oh, we didn't tell it. That's a supervised, that one.
Right.
Yeah.
Sorry. Did you kind of chunk the?
Chunking. Yeah, we just did the very basic, initial steps, just trying things that exist already. Now we're thinking, okay, how to go forward? Maybe chunking is a good idea.
Yeah, because humans, for example, like if you go through a doorway, like that just resets the learning, and it's as if it's a new episode.
I see.
So we chunk continual experience.
So we're thinking about things like surprise. Maybe that's somewhat related to surprise. Yeah. Okay.
Thank you.
Thank you.